to do harmonic series and P series. So I'm going to go over this harmonic series and P series by using a test that we don't really need for the AP test, but it does help because we could do improper integrals and show you whether or not they converge or diverge, because that might actually be on the test. Excuse me. So P series is going to look like this, where you have 1 over n to the p power. So p could be any real number. And we call that a P series. Now there's a couple rules, whether p is greater than 0, greater than 1, equal to 1, or less than 1. So when we do an integral test, what you're basically doing is you're taking the integral of the sequence, right, from where n starts at 1 to infinity of this. So if p is greater than 1, we're going to start with, and then d n. Okay, so what's going to happen here is, remember, these are improper integrals. Let's make it a b to be different, right? So 1 to b, 1 over n to the p power dn. Okay, so we're taking the integral with respect to n. Now, because p is greater than 1, it could be 2, 3, it could be anything like that. What will wind up happening is, if we want, we could rewrite it as n to the negative p, right? And if you add 1 to that, it'll still be a negative. So it'll be a negative p plus 1 this way, right? Over negative p plus 1. But we know that because p is greater than 1, and then this is still going to be less than 0, right? Less than 0, okay? So what happens is, when you do your integral, you'll wind up with like a 1 over negative p plus 1 times, this will come down, right? So because we know that this is less than 0, let's just make it a dummy variable and make it capital P, right? Which will equal that negative p plus 1. So it'll look like this, 1 over n to the capital P power. All right, and then we're going to evaluate from 1 to b. Okay, so here now, what you have is, you have this 1 over negative p plus 1 times 1 over b to the capital P power minus the 1 over negative p plus 1 times, this will be 1 over 1, so you just get 1 there, okay? Now, if b is going to infinity, then we know that this whole thing will approach 0 when b is going to infinity. So here you have 0 minus this notation here, and that will be our answer. So we do get a value if p is some real number, constant, right? So because this is real, right, we know that this is going to converge. Let me show you an example that maybe doesn't have the p in it. So let's make p equal to 2. 2 is greater than 1, right? So we'll have 1 to infinity, 1 over n squared this time, dn, right? So we're doing the limit. B goes to infinity, 1 to b, and then our function dn, right? So let's take the integral, or antiderivative. You get negative 1 over n from 1 to b. So this is going to be negative 1 over b minus negative 1 over 1, or that'll just be 1. Okay? So then what you wind up getting here is this thing will go to 0, right? Bottom heavy. 0 plus 1 or 1. So because you get a number, it converges. All right, now let's make P equal to 1 this time. Okay, so if P is equal to 1, right, we will have this notation here. Now, again, I'm not going to go through all this work again, but you get the idea. What would be your antiderivative of 1 over n? Well, that's going to be ln, right? So let's go back to this, and we have ln of n from 1 to b, right? So our limit, b goes to infinity, we get ln of b minus ln of 1 is just 0, okay? Now the limit as b goes to infinity, even though it's very, very slow, this gives us infinity. So we would say this one diverges. And the last one I want to do is, let's say, let me go over here. P is less than 1. So let's just pick P to be 1/2, right? So if P equals 1/2, we could go from 1 to infinity, 1 over n to the half, right? So I'll do the same thing. Your antiderivative, remember this is -half. So we add 1, right? You get n to the 3, nope, to the positive half, right? And then multiply by the reciprocal, so you get 2. So now I have the limit as b goes to infinity of 2n to the half. And now when you plug in, you get 2b to the half minus 2. Okay, well, approaching infinity, this is still approaching infinity, even though it's very slow. So you still get infinity. So we would say that when P is less than 1, this diverges. Okay, so the rule is, all right, when you're thinking about a P series, okay, P series, it looks like that, okay? P is any real number. Okay, if P is greater than 1, series converges. If P is equal to 1, series diverges. And if P is less than 1, series also diverges. Now, we're going to talk about one specific, okay, is this one here, okay? That one there is called a harmonic okay, it's called a harmonic series. Now, for a harmonic series, when we go back to doing the limit, right, ln is always a very slow moving function. And you could see that like this diverges, but very, very, very slow, okay, very slowly, okay? So even if you went to like 1,000,000, you probably could get a sum that is reasonable, but it does eventually diverge just because it's going so slow, okay? And just to take a look, you know, at a harmonic series, right, it is, you know, you would think that it may approach some finite number, because really, if you think about that integral test that we did, right, here's our function, like think of this as 1 over x, right? At 1, 2. So it's not so much a function, just think of the values that you're getting. Now, because we were doing the integral test, you could see that eventually this thing does grow and grow and grow. This is really, really important in the sense that we need to know that this diverges. Okay, harmonic series always diverges. Okay, now when you're looking at the different values that you get, right? So just take a look at the values that you're getting. It's going to be like 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. So this is why it converges so slowly, is because you're just adding a fraction, but it just continues on forever. So it's never, 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 never going to converge. All right.